All right. So actually, part 3 will kind of get us prepped for what we're kind of easing into with regard to measurements in the lab tomorrow. So this is all good. Density is a property of matter. Density, I like to say, is kind of like how compact or how fluffy an object is. If you were to look at the atoms squished together or look at the atoms that have a lot of space between them. We here in physical science versus biology maybe use the symbol rho instead of D for density. So I'm going to be looking for rho, looks like a P, like kind of a cursed P. So in order to calculate the density of an object, and this is what you're going to do tomorrow, all you need to do is isolate that object, snag whatever, you're going to use scales to get the mass of that object of interest, and in one of a couple of ways you're going to get the volume of that object. Okay? So then you're just going to do a quick division problem and you're going to get the density. All right? So there you go. So density is how kind of dense something is or how fluffy something is. Now, one of the things about matter is that in general, as you cool matter down, let's start with a gas. You cool gas down, actually it's going to occupy, with the same pressure anyway, a smaller volume. Okay? If you take a liquid and you cool it down, it's going to occupy a smaller volume, stay a liquid. If you take a solid and you cool it down, it's going to occupy a smaller volume. Now, as my hands have gotten closer together, guess what? My volume's gotten smaller, but my mass has stayed the same. Okay, so density is a ratio of mass to volume. Okay, so if my mass has stayed the same and my volume is changing, specifically as we get colder, the volume is getting smaller and smaller and smaller. We're dividing by a smaller volume, so that means as it gets colder, density should increase or decrease? Increase. Yep. It kind of makes sense mathematically, and it kind of makes sense just kind of what you just think. I was squishing it together. Okay. So one of the things, since volume will change with temperature, okay, density is somewhat dependent upon temperature. So that's all I'm saying. And as it turns out, solids are the least susceptible to the volume changing with temperature, although that's honestly why when you make your concrete slabs, you know, if you're going to make a sidewalk, you do one square here, one square there, one square there. That's why you put the little break between the squares so it can expand when it gets hot and, you know. Liquids are a little more susceptible to changing volume with changing temperatures, okay? And gases are the most. Like, as you probably already know, gases, it's not only temperature, but it's also pressure that the gas is exerting. But assuming you're staying at the same pressure, boy, that volume will change a lot when the temperature changes. So that's why we have a couple pieces of glassware up here. This one right here with this long neck, I don't know if we, that's actually called a volumetric flask. I can't remember when we checked in if we looked at one of those. A volumetric flask is kind of like a pipette. Remember I showed you the pipette where you're not supposed to suck it, you're supposed to use a pipette bulb? Okay. It had one gradation mark on it, and that's the same thing with a volumetric flask. Up at the top of the neck, it has one mark on it, okay? And the capacity for this one is 1,000 milliliters. Okay, actually it's probably, if you look at the, I don't know if I can see it or not, but depending upon the grade, this is actually 1,000, you know, might be 0.00, you know, plus or minus 0.01. Okay, so it's really can be pretty accurate. My point here is notice that it says TC. TC means to contain, and it gives a temperature. So it was calibrated at particular temperature. So by golly, if you need 1,000.00 milliliters at a temperature of maybe 30 degrees Celsius, that's not going to do it for you. That's my point. So down here we've got This is actually, I showed you guys a pipette. This is actually another pipette. Instead of just one gradation, it has multiple gradations, and actually you guys will be using that this semester too. So, and this one doesn't say to contain, it says to TD, that's to deliver. So that's kind of how that works. But it gives, again, 20 degrees Celsius.
Okay, question.
Uh-huh.
You said the volumetric glass, this one in particular, is calibrated for 20 degrees Celsius.
Mm-hmm.
So that means you couldn't use it for anything, I mean, is there a range that it's appropriate, or it has to be?
Well, we
or
use
like
them.
up to that?
That's a good
Is
question.
that, I mean, how does that work?
That's a good question. It depends on how kind of persnickety you need it to be with regard to, you're probably going to use
Just
a,
in general. Like you can use it up to that?
it's
Or-
probably maybe 5 degrees on either side. I'm just guessing, maybe 15 to 25 degrees Celsius, which is quite a range. The chem lab, even when it's hot, runs about maybe 23. And when it's cold, it's about 19 or so degrees Celsius. So we're kind of running in the range. Yeah, we're in the range.
And would it depend on what you're measuring? Because some things.
That's
Take
true.
more?
That's true. Some things are more susceptible to expanding when they're warm and contracting when they're cold. So it does depend upon what liquid you have in there. Assuming we do a lot with the solvent being water, we do a lot of aqueous solutions. So you can actually kind of correct for that, I guess, if you needed to. It's an interesting question.
So just, it would break?
No,
Or-
no, it wouldn't break. It just would be kind of falsely, it would give you artificially.
Not accurate information?
The volume is accurate. It's just that, how do I say this? Yeah, the amount. If you filled it up while it was hot, for instance, and then you went into normal room, that would shrink down, and it would look like you have less than a liter. Well, you had a liter when it was hot, but you don't have a liter when it's cold. Yeah, so that's a good question. Mm-hmm.
Does altitude affect it? So like say you were in a lab in like Denver as opposed to somewhere at sea level, will that affect it?
I've only heard of what elevation you are, sea level or up a mountain. I've heard of that affecting your gases, but not your liquids like that.
I just
So,
wasn't sure. What that
yeah,
was.
that's a good question too.
Are you planning on going to Colorado? For,
I'm planning on doing a lot of experiments on mountainsides. So.
Well, I like it.
well, she went to, I forget.
Yeah, I went out to Wyoming. I was out in the highlands.
Grand Canyon, yeah. Did you walk on that thing where it's glass and?
Oh, no.
Oh, okay.
I was in Yellowstone further north,
Yeah,
and I
okay.
don't think I could stomach that.
What is that?
There's something that goes out over the Grand Canyon. It's a glass plank.
Kind of like Willis Tower has that little ledge you can stand out on, and
I
it's
was
glass
thinking like
bottom.
Indiana Jones.
I wonder if they had, because I went there about 10 years ago and it wasn't there.
Ah.
I do it for money.
That's really neat though.
I'm pretty sure it does that. It does have that glass thing. 'Cause my uncle went there beginning of this year.
And he spoke of the glass.
Yeah, he has pictures. So.
They didn't pay him to do it, though, I don't think,
I'd make it
Joshua.
up if it was glass. I'd be like, look at this.
So this is actually just kind of simply trying to tell you how water, for instance, when it's cold, water will sink when it's cold relative to the water around it. So all you basically think of kind of a dye that was kind of put on the top here into the water, and then we put an ice cube on top of that, and then the water around the ice cube gets cold, and then artificially, just kind of in the water in the vicinity of the ice cube is cold and more dense and starts to sink. Our daughter's a senior this semester, or this year, whole year, and she's taking biology, and she, at dinner, was asking about the density of water. And so it's most dense about 4 degrees Celsius. And so my husband's like, yeah, that's pretty cool. It kind of turns over, and then, I don't know. Anyway.
Your husband into sciences as well?
Yeah, if you see a second Snipes in the SCC faculty, he teaches chemistry at the other campus. So we're dueling sections here.
So your daughter comes by it, right?
Yeah, poor girl. She comes by it naturally. So density is a great property of matter. And it's an example of a property where you don't have to do any chemical reactions. You just have to get a mass and a volume. But even though you're getting mass and volume, which are two extensive properties, when you take the ratio, actually it's an intensive property. Remember, intensive is independent of amount. And you could prove this to yourself as if you had like a bathtub at 20 Celsius, of full of water, bathtub full of water, 20 degrees Celsius, and you had a cup at 20 degrees Celsius, okay, the densities of those two, the water within those, the cup and the bathtub should be the same because it's the same temperature. So it is independent of amount. So since density is a ratio of mass to volume, we're all about units in physical science. The units of your answer when you calculate a density are always going to be some units of mass, and grams are great, okay? And then some units of volume. And notice that I have a couple units of volume here. I have milliliters or I have centimeters cubed. And tomorrow you're going to actually be kind of playing around with both of those to get the volume of your object of interest. So you kind of see a few other things here. This is kind of what I call the flat, G/ML. That's the flat, kind of works great in your report. But these over here is like if you're going to work your problem. You have to, what I say, kind of unpack your units. Because as you might remember, we're going to be talking about this, we're going to have units cancel that are in the numerator and the denominator amongst the terms that you're multiplying or dividing. This down here, I don't use this convention a lot, but it's sweet. So basically, this to the negative power means it's in the denominator. So to the negative first power means it's in the denominator to the first power.
Is there some sort of preferred convention for, like, milliliters will measure liquids or gases and cubic centimeters will measure solids, or not really?
Probably. That makes sense to me, that the volume, liters, we kind of think as something that's sloshy.
Right.
We can put it in a measuring cup, like a
don't
liquid
really
or
care
gas.
either way?
I don't really care either way. And something that's rigid, you would probably try to kind of get some centimeter information on it and multiply what you need to get the volume. But either way, either are great. What's the relationship, by the way? Did you guys tell me? 1 milliliter is equal to how many centimeters cubed? 1. Exactly.
We delegate him to answer that question every time.
Okay.
Isn't that two?
Yeah.
Well, that could help. So, like, if you're on a test and you're like, you need that relationship for a test, you're like, come on, Joshua, just kind of channel it. Okay? So we're going to do an example here in class, kind of akin to what you guys are going to do tomorrow. So, like I said, set an object aside, find its mass, find its volume, and do a division problem. Don't forget your units, and that'll be that. Oh, and then don't forget to round, according to the rules we talked about before. So the example we're going to do is a block of sorts. It's an alloy block, and the 3 unique dimensions are given. So we know to the nearest, 100th of a centimeter, all 3 dimensions. So how are we going to get volume of that thing?
Well, first we're gonna multiply, we're gonna get the 2.21, 1.05, 0.76.
Is that kind of what you said? We're just going to multiply all?
Is that length times width times height?
Yes, same thing. You guys are saying the same thing. Length times width times height. That's it. And the mass is there, so how hard could it be? And it's not that hard. So we have an option here. I'll kind of show you what our options are, though. So length times width times height. One of the things now, we talked about showing all of your work. This is where I would want to, you should show this, you should write these 3 dimensions down and show me what you put in your calculator. So this, by the way, is not only when we put it, and I think I'm gonna grab my calculator, I see some of you guys grabbing yours. We don't wanna just focus on the number. What I usually focus even more on at different times when I'm working the problem are the units. So what are the units to this problem? Centimeters cubed, very good. Okay. I stole my daughter's calculator from last year. It's last year, so, and she didn't like it because you had to keep charging it off, so I think she's gonna do something else. I should check into that. Okay, so did you guys get 1.76358? Okay, good. And you guys told me units are centimeters cubed. So I'll just go ahead and write that down. Now, here's your options. You can round that now, or you can wait. And you'll get two different answers. 76358 centimeters cubed. If I was going to round that now, show with a sign of fingers, how many significant figures do I need to round that to?
3.
Why do you say 3?
Probably only 2.
Uh-huh, he changed his mind. Okay, I'm thinking 2.
Oh, I
So,
thought you meant total.
I
so,
was agreeing with him, he's usually
so, yep. No, he's only right about the centimeter, cubic centimeters only. So I'm gonna take 2. So if I were gonna round this now, I would get the volume is equal to 1.8 centimeters cubed. Does that work? Okay. So now all we gotta do is do a ratio. We're gonna basically take that volume, plug it in there. We don't do a lot with like formulas. And we got the mass, we're gonna plug it in there.
Why would you do 1.8 the least precise is to the hundredth place?
Remember, since if we're multiplying like we are these 3 terms, we count significant figures. So I have 3 sig figs here,
Oh, there's 2
and
in
3
point
here,
six.
yeah, and I have 2 here. Yep,
Yeah.
answered your own question. Yep. Okay, so then all we gotta do is plug them in, okay? So carrying the information from the previous slide, the grams were already given. So density here is that mass that was given, 3.94 grams divided by 1.8 centimeters cubed. Okay, and just for kicks, I'm gonna go ahead and do that on my calculator. 3.94 divided by 1.8. Okay. Sometimes, by the way, and I'm kind of running out of room over here, I have more paper. I actually write equal sign. I write the word calc over here. Calc in my notes means it's what my calculator said. My calculator just know everything. And so it didn't finish rounding it. So I got 7.74 repeating. Does that look right? Okay. And units would be, what do you think?
Grams per centimeter cubed.
Yep, grams per centimeter cubed. I know, I'm kind of running out of room here. That's what my that's what my calculator said. So I'm dividing, so how do I need to round according to decimals or significant figures?
Same for multiplication.
Sig figs. Need to round according to sig figs.
This would be 2.
So I'm going with 2. So I'm going to click this, and I know it's kind of squishy over here, but to me, then I write A and S for answer. That means I rounded it, and I'm looking at 7.7 grams per centimeter cubed.
Do you want us to do the calc and then the answer?
So that's where my point comes in. So I went ahead and advanced the slide. Oh, no, you don't have to. That was a different sign. You don't have to, but I just do because then I don't have to think so hard. But now I went ahead and revealed the answer. Why is this not 7.7? Because we rounded the 1.8. This is exactly, I think that's exactly what you're saying. You actually have a choice. You can go ahead and use that. I don't mean to make life complicated for you. 7.7 is an awesome answer. If you want to, you can use the unrounded value. Just remember that you're carrying through 2 sig figs from your original volume calculation. That's the only catch. Any questions about that? So I would take either.
So you would accept 7.7 or 7.9?
Yep, that's my problem to figure out.
Excellent.
Which one, okay, but probably intuitively, which one's probably a better answer?
7.
7.7.
No, actually 7.9 is better. We round at the end. You kind of carry that, you know.
Well, what if you were working with a volume that had been calculated previously, then you wouldn't have the benefit of knowing that that was a significant
That's true.
failure error.
You're just, yep, we're just privy to how that volume was obtained, yep. So, in which case, you don't have a choice.
Right.
Well,
Yep.
in which case they would probably be showing another digit or what could possibly be plus or minus 1. If it was that serious of a situation.
I think I know what you're saying.
Don't worry about it.
Yeah. But are we all on the, and so sometimes your answer won't exactly match up with mine for this reason.
So, and when you get to your final answer, you remember that you rounded up 0.1 previously, so you add that 0.1, or no? I don't think so.
See, oh, to me, what, you know how calculators are? You can actually just kind of, I could have stored this number in my calculator, and then I could have said 13.94 divided by recall.
Yeah.
And then I would have gotten, and I didn't do it, but I would have gotten a number that giving me 2 sig figs is 7.9
Okay.
grams per cubic centimeter instead, yeah.
So in situations in the future, you're closer to what the exact value would be if you did everything all together. And then you
Yeah.
rounded it to
You're kind of playing with fire if you do though, because it's easy to look at this. It's easy to look at 13.94 divided by 1.76358 and think, oh, I got 4 sig figs. But you don't. Do you know what I'm saying? So I try to tell students I would round it and then plug it in, just so you'll get an answer that's. Because I'll dock you on sig figs before I'll dock you on, there's nothing to dock. Okay?
And that's why you want to see all of our steps.
Yes,
So
good
you
point.
know
That's,
which
I want to
path we
be,
took.
yes, if I see all your steps, I'm more likely to think, oh, that makes sense, or oh, they were totally with it. You know, if you just write down an answer, it's like there's nothing I can do about knowing that you knew what you were doing. All right? There's not a lot of things in science that's squishy, but that's a little squishy.
But
So,
the answer then is what?
either.
Either 7 point,
Oh, sorry. Either 7.7 grams per centimeter cubed or 7.9 grams per centimeter cubed.
just making sure, because I just got some random number.
Okay, well that probably wasn't,
Just
yeah.
checking.
So we're going to talk more about having units cancel that need to cancel, and we're not really doing that right now. But what we are doing is making sure that the units, like this is a ratio of mass to volume, well then the units in our answer need to be mass per volume. So we're just making sure we carry that through. Okay, so the density of water at 4 degrees Celsius, water is most dense at 4 degrees Celsius. Isn't that weird? Okay, and it is almost exactly 1. So it kind of looks like this. And I'll go ahead and make my little arrow means that memorize. So you're going to want to memorize the physical property of water, H2O, density of water, at 4 degrees Celsius. And like the slide says, you can go with 3 sig figs, 1.00 grams per milliliter. Okay, so you're going to want to memorize that. That can come in handy when you're working problems. That can come in handy tomorrow.
I was going to say, on a test or a quiz.
Yeah. Yep.
So if a problem asks for like the density of water, we need to use it in the problem. Are we to assume that it's at 4 degrees?
Good point,
What does it
yes.
say?
Yes, and we're going to assume it's at 4 degrees, which brings me up to my 20 degrees Celsius for the glassware. Don't get me started, or welcome to my world. Yeah, but we're gonna go with the density is 1.00 in a problem or in deep water, density of water. Okay, cool. Well, here's a graph, and there's 3 sections, so I kind of hid part of the graph. So notice that down here along it's been a while, down here along the y-axis, if we go from right back to left, it's getting colder. You guys buy that? So it's getting colder. Okay, so this first segment, water is in this liquid state. Notice as I get colder, what's going to the density? It's going up, yep, along the, did I say that wrong?
You did.
Oh my gosh, I did, thank you. This is X, that's why. Okay, so along the x-axis, thank you. Oh my goodness, it's been a long summer. Along the x-axis is temperature, it's getting colder. Along the y-axis is density, thank you. And as we get colder, the density's going up. That's cool, and that's about 4 degrees Celsius. And that's about 1. That's what we just said, okay? So about 4 degrees Celsius to the freezing point temperature, which on the Celsius scale is 0, those cute little liquid water molecules start to kind of get organized. So they're going to fluff out, basically. It is so cool. They're going to form this crystalline structure we call ice, okay? So notice that as we get colder here, what's happening to the density? It's decreasing, exactly. And this is so cool. Right as it solidifies, okay? Check that out. Check out that jump. Now, granted, along the y-axis, the scale is pretty blown up. In fact, it's blown up, but you know what that little kink right there means, right?
Yeah, it's a break.
We're skipping some, yeah. So that is crazy. So it goes from being a density of, a little bit less dense than 0.999 grams per mil, clear down here to 0.9170 grams per mil. Okay, so that's really fluffy. That's why ice floats. That's so cool. So, but what happens as you take ice or take water in a solid form and cool it down? What happens to the density?
It goes back up.
It goes back up.
Now, will that density ever reach 1 gram per milliliter again? Or will
That's a
it
good
be
question. I don't think so.
What are you talking about, just because of the process of melting, losing anything?
Well, just because he's saying it's a solid state and it's gonna get more and more, the molecules get more and more closer together as they slow down and it gets cooler. No, I don't think so.
So
Interesting.
when does it
Yeah.
hit the state where it's going negatively exponential?
What's that?
Where does it hit the state where the ice is hitting the asymptote?
Like, is that gonna just keep going, or does it hit something and start to curve down again or something?
I don't know. That's a good question. As far as I know, it will just gradually, and it might there might be some, you talk about asymptote or whatever, it might just kind of just sort of, you mean just kind of flatten out? Yeah, I think that's what it does.
I don't wanna throw a wrench in the whole works here. but
Okay.
You know how they always tell us that ice, when you fill an ice cube tray, it actually gets higher as the water freezes? They increase in volume as,
Oh, yeah.
ice cubes are bigger in volume than those
Right.
in water. So, I mean, is that in that?
Yes.
graph?
Yep.
I don't really see
That's
it.
where it fluffs out, right here.
Okay,
The volume is greater for the same mass.
and,
Yeah. This is why your soda pops, you never put a can of pop in the freezer. Because when it's liquid, it will occupy a certain volume, and when it's solid, it will occupy a larger volume. Yep, it'd be less dense, it fluffs out. Yep. You got it. So this is kind of the same deal. This actually is just kind of broken down for the stuff we were looking at the tipping point, 0 degrees Celsius. If it's a liquid, it has that density. If it's a solid, it has that other density. Gotta love it. Oh my goodness. So I think the point here is basically we have 2 rocks that have similar volumes, so that guys left and right hand is similar volumes, or not rocks, excuse me, one's not a rock. But,
Those packing peanuts.
yeah, they look like packing peanuts. It's that white kind of rock that looks like packing peanuts. So you, so obviously this one weighs more. So it's more, the mass is higher, so the density of the other one, this one here on the real rock, is more than the styrofoam. Then we have 3 substances here. We have liquid water and the styrofoam and the rock again. And you can see they're separated by densities. Okay. So the last part of this, all kidding aside, wait a minute. I think we'll leave that, because I forgot to make screenshots of those and look at those. So I think we'll leave this, if you're okay with it, we're just gonna leave that last topic for Friday. So Friday we'll finish part 3, and what?
We're
This,
gonna leave this
yes. So there's no assignment that's due Friday. So Friday we'll finish this, so there'll be more due for Monday. We'll finish this and start the next part 4. Okay? Awesome.
We're not in school Monday, Labor Day.
Oh, there you go.
Glad
So
some-
you'll have an extra little bit of time to do whatever we get to in
Tuesday.
I've taken all online classes so far.
Wednesday.
So we don't have holidays, so I
Why
probably
Wednesday?
should have.
Because we don't have class.